Hi, Phiala.
Hi, how's it going?
Good. How are you?
Yeah, pretty good.
So I'm just we're gonna have our student AV assistant connect up another laptop to the big projector. So he's just doing that now. We got you hooked into the sound and video. Make sure everything's good to go. I think for questions, what we're going to try to do for your first lecture is just run a microphone around, and I will. Let me see. I think I will just raise my hand on here to let you know there's a question, and then you can call on them if that sounds good.
Okay. Yeah, that should work. I also have the Slack open here, um,
Okay.
but
I can. I'll
live
tell them to
live
drop
is
questions,
good.
and I can tell them to drop questions in there too, and we'll see how they respond.
Yeah, either way is fine. I mean, live's sort of better, but
Okay.
you can see how it works. Zoom lectures when everyone else is in one place, so notoriously awkward.
Well, we'll try to make it as good as we can. But
Yeah,
um,
sounds good.
let me. How do I raise my hand on here? I have to remember how to use the controls.
Reactions.
Actions. Oh, there we go. Okay. So what I'll plan to do is I'll be connected on here. I'll be muted during your lecture, but you'll just see. I'll raise the hand if someone here has their hand raised, and then you can call them.
Okay, sounds good. I'm sorry you have to sit through them.
Oh no, I mean I was planning to be here for the whole lecture anyway. So
If I don't see you for whatever reason, also just let me know that someone's got their hand up, please.
okay,
If
sure.
it like goes an awkwardly long time without me saying something, it probably means I didn't notice.
Okay, we'll break in if that happens. Yeah. Okay. Let me go check on the setup on the big screen. Give me a minute.
Okay.
You have a microphone that's not the laptop.
So these microphones should
I'm happy to test it if you think it'll work.
yeah. I think yeah, I mean you can test it. Let's
Turn the
see.
video back on.
I will thank my accelerator physicist for accelerating.
Okay. Not this one.
So I think we're gonna have to plug in something else to get the right?
Right,
Certainly.
right.
Let me guess as to which one.
Is it okay? This one is for. Let's see. I'll just.
That's not the clicker.
Because I already have Lattice.
Okay.
Everything has an active.
Okay. Is this working? We're on the room microphone now. Can you hear me, Phiala?
Yes, I can hear you.
Great, we can hear you. I'm now walking away from the computer. Can you still hear me?
Well, not right now, but I don't think you're talking, right?
Okay, but you heard me say that, so you can hear me right now?
I did.
All right.
Yep.
I think everything's working then. Great, so we'll start in about 4 minutes. We'll introduce you briefly and then I'll let you get started.
Okay, no worries.
Another few minutes.
If I write at this sort of size, is it legible in the room or too small?
Yeah, probably a little bigger than that, actually. We're trying to
Okay.
make the display bigger, but probably a bit bigger than that. Okay. It is 3:45, so let's go ahead and get started here. And we have a little bit of extra instructions to begin this one, but we first introduced our lecturer. So we're very happy to have Phiala Shanahan joining us. We had hoped you'd be able to join us in person, but unfortunately she was not able to travel here. So she's going to be giving her 3 lectures over Zoom. She's from MIT, and she's going to be telling us about lattice gauge theory. Since this is a Zoom lecture, the only way that you can ask questions and be heard is on microphone. So I have a microphone, Oliver has a microphone. The way that we're going to try to do this is if you have a question during the lecture, just raise your hand. We'll bring you the microphone, and I will raise my virtual hand on Zoom to let Phiala know there's a question. So raise your hand, you get the microphone, and then Phiala will call on you. I think you can also drop questions in the lecture channel on Slack. Keeps well, but it's preferred to ask the. All right, I think those are the instructions. So with that, I'll let Phiala begin.
Okay, thank you very much. And first things first, my sincere apologies that I'm not able to be there in person. I know remote lectures is not what you signed up for. It's not what I signed up for either. Unfortunately, this was a last minute decision for medical reasons. I'm expecting a baby in July, and things evolved in a way that it wouldn't be sensible for me to travel right now. So at the last minute, I had to make the call to stay here. I know that in-person interactions are a really important part of TASI, and it's unfortunate we're going to miss out on that. So to try to at least give some opportunity, I'm going to have some office hours over Zoom. So tomorrow at 12:15 to 1:15, feel free to just drop into my Zoom room, which I'm writing down here, mit.zoom.us/my/Phiala. And if there's lots of people asking questions, you can come and chat about the lectures or about anything else. I can set up another Zoom office hours on Friday if there's interest.
Phiala,
Okay.
This is Oliver, one of the organizers. I'm going to suggest maybe writing 3 times as big as that, something like that, so that you can see it on the screen.
Okay. And we won't fit a lot on a page, but we'll do what we can. Is this better?
Better, yeah. I think that's visible from the back where I'm sitting.
Okay. Let me write out the Zoom room again.
Oh, the question is this East Coast time? Your time's here?
No, this is your time. That's Boulder time.
Okay, so that's Mountain Daylight Time.
Correct. Okay. Yeah, good question. Thanks. Okay, so these lectures are about lattice gauge theory. Okay, and what I'm really hoping you'll get out of them by the end of the lectures is a sense of how lattice quantum field theory calculations are done, what's easy, what's hard, and why. And for me, sort of most importantly, what I want to convey is a sense for how to think about, how to evaluate, how to compare lattice calculations. So for most of you who won't work directly with this set of tools, if you see a number in a paper that's coming from lattice, how do you assess that? What do the uncertainties mean? How can you compare it to other numbers? How can you compare it to experimental results? And so that's really what we're hoping to get to. Sort of the sketch of the 3 lectures is in lecture 1. So today we'll talk about what is lattice quantum field theory. We'll start, before we get into any of the mathematical details, we'll start with a sketch of a lattice quantum field theory calculation, so we can sort of see where we're going and get the big picture before we dive in. And then we'll start diving into a little bit of the maths. So we'll talk about Euclidean discretized path integrals, since the approach is built on basically a path integral approach to field theory. Then sometime either at the end of this lecture or the start of the next lecture, we'll talk about how to define lattice actions. And the choices and complications that come up there. How to think about observables. And intuition. So what's easy, what's hard, and why. And then in lecture 3, we'll get to sort of the most interesting part really about phenomenology. So it will depend a little bit how much we get through in the first 2 lectures. I'll probably give an overview of the general scope and then go through one example in some detail to really give you a sense for one state-of-the-art lattice QCD result and what goes into it. But the sort of broad picture is QCD thermo, hadron spectroscopy, hadronic matrix elements, hadronic interactions, and field theories beyond the standard model. And I want to at least touch on the sorts of things that you might calculate for each of those classes of applications. Okay, so this is the picture of where we're going, and let's dive in. Okay, so what is lattice quantum field theory? Okay, so taking that statement sort of at its most literal, lattice quantum field theory is just quantum field theory defined via a space-time lattice regulator, right? So it's just a way of defining a quantum field theory that's different but equally valid to say definitions through DIMREG. Okay, so let me just write down what I just said. It's a different but equally valid to define or to access a quantum field theory compared to other regulator schemes. So dimensionally regulated quantum field theory. And as with any sort of choice of approach, some things are easier to work with and consider in a lattice regulated version than in DIMREG, and some things are harder. So and by things, I mean aspects of the quantum field theory, really. So for example, on the harder side, well, if you use a lattice regulator, then you're breaking Lorentz covariance. And you need to be careful on how you get it back in the limit as you remove the regulator from the theory. On the side of easier, well, using a lattice regulator, you have a definition of the field theory that's valid for all coupling strengths. And it's very convenient to do numerical calculations at all coupling strengths. So it's something you can use even in the strong coupling regime, right? So e.g., again, just writing down what I said. So lattice breaks Lorentz covariance. And so you need to be careful on how you get it back again. Can I just check in on the text size? Is this legible?
I see some thumbs up around the room.
Excellent, thank you. Okay, And on the easier side, what I said was that it's a useful definition even for large couplings. And as I suggested, that's very convenient if you want to do, say, numerical evaluation of physical quantities. So okay. It's also very useful that these numerical evaluations are systematically improvable. So particularly compared to some sort of models, you can really define, and we'll see this as we go through, a series of calculations you can do such that rigorously, if you take all of the right limits, you recover the field theory that you're trying to study. So even though you start with a lattice regulator, you can recover quantum field theory results. And that, as opposed to this sort of formal definition here, is usually what people mean when they say lattice quantum field theory. They usually don't mean the definition of the field theory with a lattice regulator. They mean quantum field theory results got at numerically via a process of using a lattice regulator in the numerical calculations, right? So that is usually what people mean. So usually the term lattice quantum field theory, LQFT, is used to refer to QFT results, as in the underlying field theory, but obtained through numerical calculations of a lattice quantum field theory. And often this is also including taking the limit where you remove the lattice regulator. So the idea is that you're getting at results in the underlying field theory, even though you're using a lattice regulator to get there. Okay, of course, one of the really powerful applications of lattice quantum field theory calculations has been in QCD. So lattice QCD really has a central role in particle phenomenology. We'll see lots of examples in lecture 3, but just for example, it's now critical to the determination of the parameters of the standard model. So there are precise, systematically controlled lattice QCD results. And you might pick up in these lectures, I have something of a bias for lattice QCD. So my default example will be essentially thinking about QCD, so SU3 gauge groups in 4 dimensions. Although of course you can think about lattice quantum field theories for other field theories too. And this is actually quite satisfying to say, this statement here, because I'm quite sure that when lattice was first lectured about at TASI, I've looked at some of the old TASI lectures when I was a student and so on. This wasn't quite true yet. And over the decades, it's really evolved. Lattice QCD is now a very precision tool with great systematic control, and this statement has been definitively true for quite some time now. So, for example, critical to the determination of parameters of the standard model and so this is really because, especially in the non-perturbative regime, Lattice QCD is the only systematically improvable tool that we really have, right? So for this particular example, to give you a feel for where lattice calculations come in, you might have some quantity that you can measure experimentally. For the purposes of this example, let's call it some measured cross-section. And if we want to be very, very concrete, okay, say something like b to pi or L nu, you know that you can relate that to some kinematic factors, some CKM matrix element, and some hadronic matrix element. ME here means matrix element, right? And for this particular example, the CKM matrix element could be, say, VUB. And so then if you want to extract this, so our standard model parameters, in this case, the CKM matrix elements, you can measure this. Well, you can figure that out, but you need this. And lattice QCD calculations then come in here. You want these non-perturbatively. And you can get them using lattice QCD calculations. So that's where in this sort of a pipeline, when I'm talking about parameters of the standard model, just one example of how lattice calculations come in. And as I said, we'll discuss other applications in lecture 3. Okay, so now I want to go into the big picture. So sort of the sketch of a lattice quantum field theory calculation before we go into more mathematical detail. This is really a preview. Like I said, we will go into more detail, but I want to give a sense for how this works before we get bogged down in the maths. So okay, so sketch of a lattice quantum field theory calculation. So it really all starts from the Euclidean space functional integral formulation of field theory. Okay, so if we're talking about functional integral formulation of field theory, right, everything is encoded in the partition function. Okay, so here, these A's and psi's are just the quark, the gauge quark and anti-quark fields, right? So A, psi, psi bar, gauge, quark, anti-quark fields. I haven't written down anything about any sort of discretization yet at all, right? SE is the Euclidean action. Because we're in Euclidean space, there's no I here, right? And we'll see this much more concretely later, but you can already sort of see it here. Going to Euclidean space is very convenient because if you want to do this sort of an integral numerically, this thing just looks like something that you can sample over, right? It just looks like the Boltzmann weight of a statistical ensemble as opposed to something oscillatory if you have an I in there. Okay, but so this is where we start. And then once discretized, you'll be able to write this thing as a multi-dimensional path integral that you can do numerically. And by numerically, I mean using Monte Carlo methods. Okay, but so this is where we start. But then if you want to calculate something, well, study some physical quantity. First, you have to define what correlation functions give you access to the quantity that you're interested in. So we're in this Euclidean space functional integral formulation, but what is it that we actually want to calculate to get the physics out? So that's one of the interesting parts that we'll talk about more later, but that's really step one. So to study some physical quantity P, what we can access are correlation functions. So define what correlation functions give access to P. And this may or may not be straightforward. There may be multiple obvious options, or you may have to come up with something. You may have to invent a new one, right? So you can get quite creative on coming up with interesting definitions of correlation functions, for example, maybe involving non-local operators, and in some limit, it gives you access to the quantity that you're interested in. But this is sort of step one. Here, it's also useful to already be thinking about the precision goal of the calculation. You know, with what precision do you want to extract P in the end, as it might affect all of the next steps. Then you have to define how you're going to do the calculation numerically, and specifically, what's the discretization of the theory that you're going to use? So we're going to discretize the theory onto a space-time lattice, right? And you have choices in doing that. And we'll spend some time today on how those choices manifest. But so define the discretization of the action of the theory. So the gauge and fermion pieces that you will use. So ideally, any discretization that gives you back the continuum action in the limit as the lattice spacing goes small will work. But in practice, it does actually matter. So especially the symmetries of the action. So for example, if for the quantity you're interested in, chiral symmetry is really important because it prevents some sort of operator mixing, for example, then you really have to think about how to preserve chiral symmetry in the discretization of your fermions, right? So these are the types of considerations that need to come in. Typically, we'll discretize the theory onto a hypercubic lattice. And I say typically, but not always. You can do other interesting things. But since the calculations are so expensive and hypercubic really sort of minimally breaks symmetries, it really is the most typical choice. Of course, that means you have some spacing, some lattice spacing, which in physical units, in current calculations, this sort of lattice spacing between neighboring sites would be something like 0.04 to 0.1 something, maybe 0.15 Fermi, right? And some lattice volume. And you'll see this written typically something like this. So we have 4 dimensions, space and time. Again, there are other choices you can make, but a very typical choice is to have the 3 space-time dimensions with the same number of sites and then have a somewhat longer Euclidean time dimension. So you'll see this be something like, okay, a sort of large calculation these days. You'd have something like 128 sites in each of the spatial dimensions and then 256 sites in the temporal direction. We'll go through these scales more later also. Okay, so you've defined what correlation functions you want to calculate. You've defined a discretization of the action. And as I said, we'll go into both of these much more. Then you have to define the parameter sets for the calculation, right? And how to tune them. So that means, okay, the lattice geometry, what sort of a volume, what sort of a spacing, but also what bare quark masses are you going to use? What level of statistics are you going to use in your Monte Carlo calculations? And you really want to design the various sets of all of these parameters in such a way that you can take any of the necessary limits that you need to take. Maybe a continuum limit, maybe an infinite volume limit, maybe a limit to the physical quark masses. Because we're really starting from this discretization of the action of the theory, let's say QCD, the free parameters are the same free parameters as in QCD itself. So the bare quark masses are the free parameters. So you don't know sort of ab initio what their values should be. You have to plug in some values, compute something like a pion mass, see how close it is to the physical pion mass, and tune, right? So there's a tuning step involved, and you want to do the calculation at a number of different sets of parameters so you can take all of the right limits. So that is define parameter sets for the calculations. And how to tune them, i.e. you're going to have sets of action parameters, which may include things like bare quark masses, lattice geometry, statistical precision, and you want to choose them in such a way that you can take any necessary limits. So for example, continuum, infinite volume, physical masses, etc., with sufficient systematic and statistical control, right? Then, and this is a part that we won't talk about so much, you need to choose and optimize the algorithms that you'll use to actually do the numerical calculation and run the calculations. So I'm being sort of loose here, but you're going to numerically evaluate the lattice path integral using Monte Carlo importance sampling. You'll see a little bit more what that means later this lecture. MC means Monte Carlo here. And what that will look like is generating samples of field configurations as step one, and then calculating correlation functions as step two. And again, we'll see that in a moment when we go into a little bit more detail. Once you've run the calculations numerically, you have to do a statistical analysis for each set of parameters and do whatever extrapolation, interpolation, limits to extract your physical quantity P. So here we should be clear, of course, at each set of parameters, because you have to do the calculation multiple times typically, say for different lattice spacings, so you can take the continuum limit, different volumes to be able to take the infinite volume limit, so that what you're really recovering are results in the underlying quantum field theory. Okay, so out of these various steps, steps 1 and 2, so step 1 was defining what correlation functions will actually give you access to the physical observable, and step 2 was defining the discretization of the action of the theory. Those are, in some sense, the ones that I think give the most insight into, if you read a paper and it has some number from lattice QCD, what does it really mean? So those are the ones that we're going to talk about more than some of the others. So this is the big picture. And now I want to move on to talk about Euclidean discretized path integrals. If there's any questions about this, feel free to ask. But as I said, we're also going to circle back and talk about all this in more detail in just a moment. But feel free to interrupt, especially while I'm writing the heading for the next topic. Okay, So Euclidean discretized path integrals. So we saw this in very, very brief detail just a moment ago. In the path integral approach to field theory, it's really the generating functional that contains all of the information about the theory. So we can start with our generating functional. So let's be very explicit about this now. So I'm going to write a generating functional with some external sources. So these guys here, external sources. And I'm going to assume we have some sort of gauge and some sort of fermion degrees of freedom. And so far, I've done nothing lattice specific, right? This is just, oh, I should have put an I here really, and an integral. Excuse me for the typo. Let me correct that. Nothing lattice specific, and also not even Euclidean for now. Okay, and so this is of course our integral over all possible gauge and fermion fields. And we've just added our external sources up here, right? 3 fields, 3 external sources. Okay. We know in terms of the generating functional, any sort of expectation values, also Green's functions, correlation functions, all named for the same thing here, can be expressed as functional derivatives, right? So if we have some correlation function, and I'm just going to throw some fields in here, we can write that as some sort of functional derivative with respect to these external sources. Right, okay. So these are the sorts of things we want to compute. And we're starting from here, this generating functional. Okay, so if we want to compute this, we really have to define and interpret the measure and also regular momentum integrals. But here you can really see you have an oscillatory integrand from the e to the minus is, right? So that gives you cancellations between different phase space and numerical difficulties, also called a sign problem, right? If you're trying to do an integral over something oscillatory, numerically, you have to cancel out all the bits above the line with all the bits below the line. Canceling 2 things to get a small number is something that's very hard numerically. So we don't like oscillatory integrands. So that's where the Wick rotation from Minkowski to Euclidean space really saves you and gives you a probabilistic interpretation instead. So getting rid of the I is really critical here. So there's an oscillatory integrand. From e to the minus is. So you get cancellation between different regions of phase space. And numerical difficulties. And so it is very convenient to do a wick rotation. So send t to minus I t Euclidean. To give you a probabilistic interpretation. And by that I mean the exponential, so this e to the minus is, if you get rid of the I, just looks exactly like the Boltzmann weighting of a statistical ensemble, right? So you can really interpret this as a probability density. Okay. Now, I've said that we're going to do this integral over the various fields numerically. In fact, part of that integral you can do exactly. The integral over the fermion degrees of freedom, you can do exactly first, and then you're left with only doing the Monte Carlo part over the gauge degrees of freedom. So let's see how that works. Okay, and to see that, we really have to remember how fermions enter the path integral, so what types of fields they are. If I was there in person, I sort of like having more of a conversation, so I think that's going to be difficult, but I'll ask questions and give a second for you to think about it, and then answer them myself rather than trying to have the microphone run around. So what kind of fields are fermions in terms of their statistical properties? Right, they're Grassmann fields, right? So they're anti-commuting. So let's just remember what they look like. So fermions enter the path integral as Grassmann valued anti-commuting fields. So we have psi A at X and psi B at Y. If we swap them, we pick up a sign, right? Okay, and we can also think about what the continuum Euclidean action looks like for a single free Dirac fermion, and then we're going to just go through how we can do this integration here exactly, right? That's where we're going. Okay, so we can just write that out. Again, other than being Euclidean, this should look quite familiar. Again, Euclidean space, so these guys are both downstairs and it's okay. These guys here, these are now also Euclidean Dirac matrices. Right, so they have sort of familiar properties, but we can have the anti-commutator of gamma mu gamma nu is 2 g mu nu. Gamma mu dagger is equal to gamma mu. So other than being Euclidean Dirac matrices, this all looks just the same as it does in Minkowski space. I'm just going to rewrite this in a quadratic form for convenience. Okay. So if we think about what the partition function looks like with our external Grassmann sources, you can see that you can rearrange it into a convenient quadratic form where you can just do the integration over the fermion fields. So here's the partition function. So we've got an eta and an eta bar. We're just for now thinking about the fermion piece, so integration over the fermion fields. I wrote this in the quadratic form here, so I can write shorthand notation here and just write psi bar dot m dot psi minus eta bar dot psi minus psi bar dot eta, right? Where these guys secretly, of course, there's integrals over dx happening here and here also. It's just compact notation for what's going on here. Okay, we can change variables on this to make the whole thing look quadratic. So the shift that we made here, just as an aside, so psi prime is going to psi plus m inverse eta, psi bar prime goes to psi bar plus eta bar m inverse. And if you make that change of variables, you can see that you can now get all the size out of this second term here. And so we just have a quadratic term in the size. And now this should look like an integral that's somewhat familiar, that you know how to do. Sure, we have fields and things, but it still just looks like a nice Gaussian integral. And so this we can do exactly. And you just get a determinant of the matrix that's appearing in the middle here. So det m, and then we're left with the exponential with the size. So we can really just do exactly the integration over the fermion degrees of freedom. Now, this M inverse, so the inverse of the Dirac matrix, remember this M here is just writing out this quadratically here. This here, that now appears, also known as fermion propagators, right? That now appears in correlation functions. So remember, if I do correlation functions, I'm going to have functional derivatives with respect to eta and eta bar. If I have a psi bar psi, I'm going to have one functional derivative with respect to eta and one with respect to eta bar. So I'm going to just pull down this M inverse. So in correlation functions, you're just going to get these fermion propagators showing up. Right, so that's just coming from these functional derivatives. Plus terms that are order eta bar, right? And so what that means is if I write out like a correlation function just a little bit more explicitly here. So if I've got some, psi x1, psi xj, psi bar y1, psi bar yj. This whole thing is just going to look like a sum over permutations with some signs. So that's just combining, just contracting all of these different psis and psi bars together. You get propagators, M inverse. And you just get all possible contractions that you can write down, right? So in a lattice quantum field theory calculation, you compute fermion propagators, so these M inverses, you contract in all possible ways. And then what you're left with is still the integration over the gauge degrees of freedom. And that's the part that you have to do via Monte Carlo sampling. So compute fermion propagators. And numerically, as we'll see in a moment, we haven't talked about discretization yet, but we're about to. Numerically, on a discretized theory, this thing looks like a big matrix that's order of the lattice volume times the lattice volume. So you have to invert very big matrices numerically. That gets computationally very expensive. That's one of the computationally intensive parts of these calculations. Contract them in all ways. And then you're left with the integration of the gauge degrees of freedom. By Monte Carlo sampling. Okay, so this is sort of a little bit of an aside about the fermion part of the integral. Now let's talk about the remaining part, the gauge part. So discretizing the theory, and then what taking the expectation values really looks like. Exactly how you define the discretization of the actions, we'll talk about later. But so we're going to discretize the theory onto a 4-dimensional hypercubic lattice. Again, this is a typical choice. You can make other choices. And so let's define the lattice like this. Okay, so this A here is sitting in as a lattice spacing. This N here is we're labeling our lattice sites as integers in Z4. Right, so we've just discretized the spacetime. In practice, of course, you have some finite number of points. You don't have all of the sites in Z4. You have to define some finite volume, and you'll put some boundary conditions on that box, say periodic, anti-periodic as appropriate. But for the discretization, we can just think about the grid itself. And then what discretizing the theory means is we're putting the various fields onto, say, the sites of this lattice. So the quark fields live on the sites. So what that means is that psi x that you write down in the continuum theory is going to look like psi on n, where n is some vector defined on your hypercubic lattice, right? Integrations over x will look like sums over n. And an integration over the path integral, the integration of the fields, well, that looks like this. Now this here, that should look pretty familiar. So that is probably how the path integral was defined in your field theory class, or at least in one of the field theory textbooks you've looked at. This is pretty much how at least I introduced the path integral in my quantum field theory lectures. And there it's just a tool for defining what we mean by the path integral. Here, this is really what we mean by the path integral on our discretized lattice here. Okay, so fermion fields are easy. We'll see soon that to define, basically to maintain gauge symmetry, it's convenient to define gauge link variables as parallel transporters between sites. So for now, take this as given, but we'll see it in a moment. So it's convenient to define gauge link variables by which I mean parallel transporters between neighboring sites. So the degrees of freedom we like to work with, instead of here, our gauge fields on site X, we're going to call them U. And we'll come back to this, but here this mu is defining a direction and N is defining a lattice site. So you can really think of this as living between two lattice sites, between the one at mu and the one living at, between the one living at N and the one living at N plus one step in the mu hat direction. You can really think of this gauge link variable as living along that link. Yes, question.
Yeah, hi. This is from Ethan. It seemed like a good opportunity to make sure you could see the hand raising. This is minor, but on the D side, when you discretize the path integration, shouldn't there still be an integral symbol on the right-hand side?
Thank you very much. Yes. Thanks, Ethan. Good catching of the typo here in pink so you can see where the typo was if you need to put it in your own notes. Okay, good. So now we've put the various pieces together and we can write the expectation value. And so this is what we've been trying to get to, which I said very loosely at the start, but now we can actually see it, what expectation values look like. So we're taking the expectation value of some observable, some operator of interest. Exactly what that is will depend on the physics you're trying to get out. And we've defined our various fields now as U, psi, and psi bar. We're in Euclidean space. So we have just e to the minus s. Right? And this is what that expectation value looks like. Now we know we can do the integral over the fermion part exactly. So this thing here, this S, this looks like S gauge plus the fermionic piece, where this is the Dirac operator that we saw before. This gauge piece, this might look like, you know, if we're thinking about QCD, minus a quarter F mu nu, right? The gauge part of the action, but it'll be appropriately discretized. We can do this part of the integral explicitly. And we saw before that what we get is a determinant of M. We're left with a gauge part of the action up there. And we're left with our operator here, which is now a function of our fields U and M inverse. Remember the propagators that we saw come out when we calculate correlation functions. So this is really what it looks like. This U here really, again, looks like a product here right? So this is direction. This A label is for color. This is for the discrete volume, the sites in the discrete volume. And so what this is it may be a very large, but it is a finite dimensional integral, right? So this is what we do numerically. So you'll see that this integrand here, this has a weight factor. It's whatever your operator is times this factor here. And in practice, you really want to think about these as truly very high dimensional integrals. So in true state of the art calculations, the dimensionality can be 10 to the 9 to 10 to the 12 degrees of freedom. And so, of course, if you just do naive Monte Carlo sampling in such a high dimensional space, it won't converge at all. However, if we use this weight here as a probability measure, so we sample the space of fields with this probability distribution, so this weighting already built in, then it turned out this distribution is peaky enough that with a sort of finite number of samples, orders thousands, you can already get a very nice numerical result, even in such a high dimensional space numerically. So that's what we mean by important sampling, is we sample the most important gauge fields U, where important is defined by this weighting factor here that's weighting the integrand, correspondingly more, and the less important ones correspondingly less, hence important sampling. And what that means in practice is that we just have to sample the space of all U's with this probability distribution. Okay, so integrand has a weight factor, e to the minus S gauge, and the determinant. And again, this thing here is a order volume by volume matrix on the discrete system. So big matrix. We sample the space of U's according to this weight. So really treating it as a probability measure. And the way we do this, and I'm really not going to talk much about the algorithms we use at all here, but we do this via a Markov chain process. So you have some chain, you start with some configuration U0, you update it to some configuration U1, and so on, where the transitions in that chain are required to satisfy certain conditions so that the desired probability distribution emerges as the equilibrium distribution of the process, right? So you can define how these transitions should happen so that you get the right probability distribution in the limit of a large number of samples. Okay, so once you've done that, once you have the set of samples, so here you can see the different computational steps. One is get the samples of the gauge fields U, and then two, you have to compute observables on them. So once you've done that, actually, because we've sampled these U's with this probability weight already built in, it's just evaluating this operator O. So the observables that you want can really be computed as essentially simple averages with the uncertainties falling with the number of samples taken, like 1 over square root n, right? So the set of configurations is usually called an ensemble. And with that word comes the meaning that it's been sampled according to this probability distribution. Then you compute observables. And essentially, you're just going to sum or take the average of the observables computed on your set of samples. And the more samples you have, the more the statistical uncertainties will go down. Okay, so that's the general idea. What we're left with that we haven't addressed at all yet is, well, how do we write down the action on the discretized space? And two, what O's here give access to the physics that you want for some particular problem, and how do you construct that? Okay, so we're going to start with how you actually write down what this S here is, both the gauge part and the fermion part on our discretized space. But now is also a good time for questions. If anyone has them, again, I'm going to write a heading for the next section. It's a good time to interrupt.
So I have a question.
Yes.
For the matrix you wrote earlier, that's the exponential of the Hamiltonian, basically, that evolves the wave function. Is that correct? The U.
Wait,
or U bracket 1.
which matrix are you talking about? The U?
Yeah. Is that what
So
it is?
the U, that's no. So these are the gauge fields. So we started with gauge field variables, A's. So just like they would be in a continuum field theory. And we're going to write them, and we'll see this in a little bit more detail in just a moment. And the degrees of freedom we're going to rewrite in terms of these parallel transporters. So it's really this here, or more precisely, can you, if I write on top of this with the red, can you see it? Or maybe I'll write down here. More precisely, these U's oh dear, that went away. Let me write it again. So the U's really are just the parallel transporters here. This is the gauge field that we started with, A's, and here I'm integrating from 0 to, this is the lattice spacing A. So I've really got my discretized lattice here. I'm thinking about the U as being the parallel transporter that takes me from one side to the next side over.
Okay. In that case, when you're path integrating over the U, how do you ensure that it's a valid transporter? For instance, that it has that basically, how do you restrict it to being unitary?
So you're asking when we sample these degrees of freedom. So if we take the example of, say, an SU3 gauge field, right? Then what this entire gauge field configuration U is going to look like is, for every edge of the lattice, you're going to have a 3x3 complex matrix with unit determinant, right? And that's the space that you're integrating over, is the space of all of those configurations. So the first step, this sampling step, is how do you sample this data structure, which doesn't look like just an array of real numbers. It really looks like a matrix on each of these edges of the lattice, right? That's what one sample looks like. How do you sample that according to the right probability distribution? So the way we typically do that is through algorithms. One popular algorithm is called Hamiltonian or hybrid Monte Carlo, where how you're getting from one sample to the next is not an arbitrary, it's sort of an evolution of a Hamiltonian dynamics trajectory in a fictitious time dimension. And so that of course is not exact, and you have to do an accept reject to correct for any inexactnesses in the numerical integration that's getting there, but you can sort of ensure by that algorithm that you're not wandering out of the space and also staying having the right probability distribution in the limit of a large number of samples. That was your question, right? How do you make sure that your samples are all in the right on the right manifold?
That was it. It was how do you make sure all of the U's are unitary or unitary?
Well, you have to construct them that way, right? When you're this part here, the sampling over the U's, they have to stay in the right space. So when you're whatever algorithm you use for generating that set of samples, they have to obey all of the right properties. So they have to look like the right gauge fields for the theory you're trying to study. So whatever sampling algorithm you define better stay in the right manifold.
Thanks, Phiala. Any more? Yeah, I see one over here. Say your name and say where you're from, so Phiala doesn't feel like she's talking into nowhere.
Thank you. Thank you, Phiala. I'm Wenqi. I'm from U Chicago. So have a question about the fermions. I've also heard about, say, quenched fermions or active or dynamic fermions. Can you explain that and how those connect to what you talk about here?
Yeah, that'll be a little easier to explain later when we've gone a bit more in detail. Okay. But it's really about the question of whether you keep this determinant around or not, right? So the impact of the fermions is both that you get fermion propagators, but also that this determinant shows up in your probability measure. And so there are various approximations you can do, one of which involves basically forgetting about this determinant here, which means that the fermions aren't present in your sampling of the gauge fields, but you do put in fermions explicitly when you do contractions.
Okay, so thank you.
Any more questions right now? Oh yeah, here's one.
Hi, I'm Samuel from Caltech. I had just a quick question. So in this case, fermions, we assume that there are free fields, but if there are interactions, how do we treat them?
Oh, again, we'll see a little bit more of this later, but essentially, whatever action you start with, step one is to write down a discretization of the theory such that in the limit as the lattice spacing goes small, you recover the continuum theory that you're interested in. And how many fermion fields you have, what sort of interactions you have, what kind of gauge fields you have, that's all part of the definition of the theory you start with. Then you have to discretize it in order to define your action S. So that really comes out at sort of that stage of the calculation. And you're right, depending on exactly what your theory is, it might not look quite like this. If you have a theory with Majorana fermions, you can end up with a Pfaffian instead of a determinant. But the general principle is essentially the same.
Actually, I want to comment on that. This is not a free fermion. This is actually a fermion coupled to gauge interaction.
This is a fermion coupled to gauge interaction. That's correct. But just the fermions that we looked at here when I didn't write down gauge fields were free fermions.
And also, like it looks like if we want to integrate out fermions, they can only interact through gauge field instead of having, say, for fermion effective interaction.
Yeah, so actually, if you come to office hours, we can chat a little bit about that. There are ways of trying to deal with for fermion interactions. Actually, one of my grad students is working on a non-QCD theory with Majorana fermions and a four fermion interaction, and some of the algorithms get more hairy, but depending on exactly what it looks like, you can follow the same general idea.
Thank you.
Anything more right now? Phiala, we've got about 5 minutes left.
Yeah, okay. Good, then we'll just give a very bit of a hint of what we're doing next, which is defining lattice actions. And the idea in continuum field theory, when you demand gauge symmetry, that's where the existence of the gauge field comes from to construct the gauge covariant derivative, right? So when I teach interactive field theory, you see this in, say, scalar QED. It's basically the same in the lattice formulation. So we'll see the same thing if we want to write down a derivative, which we get, say, in a action for, we can again go back to a free fermion. You'll see that demanding gauge invariance really demands that you put the gauge fields in as the link variables. So let's start again with Euclidean, Dirac action, free fermion. And if you want to just naively discretize a derivative, the first thing you write down is write down a finite difference, right? But if you write down a finite difference for the derivative here, there's something wrong with it. So I'm just writing down a symmetric finite difference. And what's wrong with it? It's not gauge invariant, right? So if you remember what gauge transformations look like for fermion fields, where these omegas are, for example, in SU3, if we have SU3 gauge fields, this is not gauge invariant because we're going to have an omega at n and an omega at n plus mu hat, right? So if we have, again, an SU3 gauge symmetry, it's really local rotations in the color space, and these are not at the same site. So the omegas and omega daggers are not going to cancel. So this is why I said before that it's very convenient to introduce the gauge lengths as parallel transporters. So this is what I wrote down in red before. I'll write it down really explicitly here just to be clear. So if we write down these U's, this lowercase a is the lattice spacing, capital A is our gauge field. We can think about them as just exponentiating e to the I lattice spacing a mu. Then what we have for the gauge transformation property is that this transforms in the way that compensates between two different lattice sites. Right, so over here, there's an omega at n, and over here, an omega dagger at n plus mu hat. Right, so if we have some lattice, this is some site n. We think about the gauge fields as living, this would be u, if this is a mu hat direction, u mu at n. And so we think about the gauge fields as living on the links or the edges of the lattice. So with this construction, now if we look back at our finite difference, if we replace this with also a u mu in here, then we have something that's gauge invariant, right? So this would be a very naive discretization of the fermion action. And next time we'll talk about what issues there are with a naive discretization of the fermion action, but this at least gives us something gauge invariant. And it's a place we can start from. Okay, so I think I'm pretty much out of time. I'm still happy to take questions. I'm also happy to take questions in the open office hours tomorrow, which, as I said, were at 12:15 to 1:15 your time. So during the lunch break, come in and chat about the lectures or about anything else.
Great, thank you very much. Maybe I'll ask you to drop the a reminder about the time for office hours and the Zoom link in the Slack when you get a chance.
No problem.
And then just since the potential barrier was a little higher for questions during the talk, I will ask if there's any more questions right now. Yep.
Hi, I'm Yanis from UC Louvain in Belgium. So I had just a question about so you mentioned that, yeah, the standard case is to use this hypercubic lattice, and you mentioned that there are some cases where you might want to use, yeah, something else. Yeah, I was just wondering, like, when do you want to use something else, and like what type of other structure, in a sense, can you use?
Yeah, I mean, some of the simplest other things you can do is change the lattice spacing, for example, in the time dimension relative to the spacing in the spatial dimension. So we'll see next lecture that when you're extracting observables, the evolution in Euclidean time is very useful to, say, filter out excited states. And sometimes it's helpful to have a finer spacing or a longer extent. So maybe you want a larger spacing. So depending on what calculation you're doing, that sort of anisotropy is something common. Then you can also do really cool things of having non-square lattices at all. That's something I don't know nearly as much about. It's not very mainstream for large state-of-the-art calculations, but there's some really cool ideas about how doing that can give you better access to other observables, especially for non-QCD theories.
Okay, thanks.
Any more questions right now?
Hi, I'm Peter from the University of Zurich, and I'm interested in this statement, that the lattice acts as a regulator effectively, because to me, it still seems like you could, for example, have arbitrarily soft gluons that would affect your observables. So like in what sense does it, for example, regulate infrared divergences?
Yeah, I mean, well, I guess there's separate questions about regulating the UV pieces and the IR pieces, which you still have to worry about separately, depending what kind of calculations you're doing.
Right, but like just having the lattice does it like prevent you from having any problems with these divergences? I mean, in principle, infrared.
You can definitely still have divergences that you have to tame in other ways.
Okay.
So the lattice cutoff regularizes the UV divergences, right? That you then have to remove after a normalization. But the AI divergences can certainly give you problems depending on what you're doing.
Okay, I see.
All right, great. Well, maybe we'll stop there for now. Thank Phiala one more time. Is there coffee outside? Thanks, Phiala. That was great.
you. Bye-bye.
See you tomorrow.